want to get right into it? Yeah. Okay, who's familiar with Ormet? Quite a few people. I certainly know Monty is. He's kind of an Ormet pioneer here. So, for those who are not familiar with Ormet, basically it's a non-reversible solder. So it takes advantage of the fact that copper and tin form alloys at relatively low temperatures, and then the resultant alloy has a much higher melting point. So it's a kind of a solder that won't melt. The other advantage is it bonds to not only the copper particles within the paste, but also the copper interlayers. So you form an intermetallic bond with your copper interlayers. I don't know if anyone's ever heard of the Aleve process that used the copper paste. That had a binder system, and the binder system would allow the copper particles to stick together, but any change in expansion from different temperatures, you'd have a change in resistance. Whereas this alloys with the interlayer copper forms a metallurgical bond. It's kind of like sweating a copper pipe together. It forms that metallurgical bond. So really it's a tin bismuth alloy that melts, starts melting at 130 Celsius, and then at higher temperatures it starts kicking out the bismuth and forms an alloy with the copper. So I got a little video of the paste sintering. So this is really a sample of the paste put between two glass slides and put on a hot plate under a microscope. You can see the copper particles, and then what's going to happen is as the tin bismuth starts melting, it will react and combine with the copper. One thing you'll notice is this is just between two glass slides. Notice how there's no bubbles, right? So imagine this happening inside the dielectric of an inner layer or multiple layers in the lamination process of the PCB fabricator. So it's very important that part of the paste technology is the system that removes the oxide shell from the copper and allows the tin to form that alloy without producing any bubbles or any other artifacts that might affect the PCB. Probably getting into more detail than you want. But anyway, I think the technology is kind of cool. This could be used for embedding components. It could be used for high temperature assembly. So let's say your circuit board is going to be exposed to high temperatures. You're using some advanced materials that can withstand those temperatures. That's beyond the melting point of, let's say, regular solder alloy. This is an alternative for that. But it can also form Z-axis interconnects in the PCB. Probably tell I'm more familiar with this than I was with the previous presentation. So anyway, what it allows you to do is to break up the board into simpler components. And that has all kinds of implications. You could, let's just say you wanted to do that coax I was showing you in the previous, where you drill through, fill with non-conductive via, come back, drill and plate, so you have that micro coax. It's much easier to do that in these individual components than it is trying to do that in a much thicker PCB, and then you can stitch it together with lamination. Really what the Oremet allows you to do, normally when we build a PCB, we laminate, drill, plate, laminate, drill, plate. And if it's a bunch of sub-lams, as Jerry pointed out, you're going through the shop multiple times. It's like building individual PCBs all over again. With the Oremet paste, you're putting these together all in one shot. So one of the things you can do is eliminate the back drilling. So just, you build these two subs and then you put the board together. Now, if you're only back drilling once, it might not make sense, but let's just say you have multiple components and multiple via depths, then it really starts to become a big advantage, both in accuracy and in even simplifying the fabrication process. So just some examples of cutting out the lamination cycles and giving you freedom to be able to place vias anywhere you want. And again, the idea is you're forming the interconnect between the layers during lamination instead of laminating first and then plating later. So it actually eliminates the plating process. There are some mobile applications for this where you, instead of going through the plating shop 4, 5, 6 times, you only go through the plating shop once and then you put all your layers together with the Oremet. So really really reduces the need for plating and increases the plating capacity of a given PCB fabricator. There's also other benefits too. Not going through the lamination cycle over and over again is better for some of the materials, less decomposition and so on and so forth. But this has a lot of potential from a design standpoint and fabrication standpoint. So just another example, you could have double-sided building blocks and then Ormet them together. In theory, there's no limit. You want to do a 100-layer multi-layer, you can do it this way. And you're only laminating once. I don't know how many fabricators are doing that. But as I pointed out, I have a customer that builds ATE boards that's pushing up to 80 layers. So it's quite a bit of miles and miles of interconnects inside that PCB. Yes?
And will this maintain the same dielectric constant of the copper plate when you do the bond?
I think you're asking the conductivity difference, right? Between
Right.
copper, yeah, between raw copper.
IR drop.
Right, so it is not as conductive as copper metal, bulk copper metal. However, unlike a via that may not be completely plated shut with copper, the whole via structure is the metal. So you don't see that discontinuity between layers. And usually the length is very short, so it's not a problem in the design.
So essentially you can stack as many two-layer vias through the substrate. Is there a price difference in that versus?
Any fabricators here want to answer that question, the price difference?
The cost of manufacturing that?
There's a place for Ormet. It's not obviously in every design, but there's a place for Ormet, and it does add cost, but it can also take cost out depending on the design. So,
Okay.
but again, this is kind of one of those things where there's a lot of potential here, depending on the application.
Excuse me, this idea you currently saying that there are 80 layers, 80 layers.
Yeah, you can do that. So one common way is to do so for 72-layer multi-layer. By the way, this is done in production. You have 18 layer subs that are stitched together. But you could do some number of double-sided subs. In theory, you could laminate them all in one shot and have a very high layer count board and have unrestricted via placement, because you're not taking up that real estate with a via that's going between multiple layers. It has a lot of potential, but like everything else, it has its place. It's not for everything. Yes?
What's the maximum dielectric thickness that can handle?
So we like an aspect ratio of 1 to 1 or less. So in other words, if you have a 5 mil diameter via, you don't want your dielectric any more than 5 mils.
So the only negative, because I've used this on like multiple products, is to use like any layer via, you got to have a lot of layers to get to, say, if you're trying to do an 040 board, 062, it just takes a lot of layers,
But why couldn't you split that into
well,
two?
that's what we've done before,
Yeah.
but if you do it like a pure any layer.
A pure any layer this is somewhat theoretical. I can't think of a lot of designs where you'd have to do this, but
Actually, we did, it was 16, it actually worked really well. Worked really well.
This is a vehicle one of my customers did for me. This is using Itera MT40 as the dielectric, and one lamination cycle. So really, the outermost are traditional copper-plated shut vias, and all the internal vias are Ormet. So you could basically, this is a simple board, but you have complete unrestricted via placement. You can put vias anywhere you want.
For high-density boards, it's amazing. You can, it's amazing what you can pull off.
What's interesting too is the bonding mechanism, and I think Jerry will appreciate this, how it alloys with the inner layer of copper, right? So what's happening is it's literally soldering itself to this inner layer of copper, where in a traditional plated via, you're gonna have that electrolysis layer, right? So, or if you're using a direct plate system, you might have an artifact left there where you have the plated copper out connecting to the foil copper inside the board. That goes away with this. So it's something we're getting more data on, but it has some implications from a high reliability standpoint, some positive implications.
Correct. So I'm looking at the picture there, and maybe you're gonna talk about it a little deeper in there, but is that laser drilled, or how are you getting the holes in there?
Yeah, so from a process standpoint, what we would do is we would tack a B-stage pre-preg. Is everyone familiar with the term B-stage, C-stage, right? So really, you know, you would take your core material, you would print and etch the layer, then you would tack on some B-stage pre-preg, laser drill the B-stage, and then apply the paste in those openings. And then when you laminate, the B-stage melts, flows, cures, bonds to the materials from a structural standpoint, but at the same time, the Oremet's alloying, as I showed that video, that's alloying within itself and also to the interlayer coppers. So not every B stage works with Ormet. If you have high flow B stages, it can sweep the paste. I remember, Jerry, you guys built some boards, gosh, I'm trying to, was it Nokia? You built some boards where the paste just, 370HR, just, the paste just became comet tails, yeah. So the particles have to stay in place long enough to have that sintering. But we do have a good library of B stages that are compatible with Ormet. That's an area where we can help the fabricator. We know which B stages play nice with the Ormet paste. And there are more than a few. Meg 6 works, Iterum T40 works, Tachyon. DuPont has some new materials that are compatible with the paste. So there's a list of materials that will work with it. So I talked about this in the previous presentation. Yes, sorry.
Obviously, these are a little bit more exotic prepegs that you're going to have, and they're going to have a limited shelf life inside the fabrication. What's the typical lead time you guys need to get the materials and have them in time for the design?
Well, if it's a material that Insulectro has, the lead time is next day. If it's something we haven't stopped. But if it's a special material or made-to-order material, that can be a little bit different. Believe it or not, a lot of the PPO resin systems, the polyphenol oxide resin systems, actually have a longer shelf life than phenolic cured epoxies.
Okay.
So they actually, you know, so like Iterum T40 Tachyon, the pre-preg shelf life's a year. Whereas the I'm sorry?
Do our certs say 1 year?
Yeah, yeah. No, that's a published shelf life for those materials. Believe it or not, polyimide actually no-flow polyimides play well with Ormet, and they can have long shelf lives because it takes a lot more heat to cross-lengthen, right? So room temperature, nothing's happening in that material. But most board shops now have temperature-controlled storage, but that should not be a showstopper.
And humidity is the killer.
Yes, well, that's a whole nother subject. That's a whole nother presentation. But yeah, we work with the board shops a lot, the fabricators a lot, to help them manage the moisture in the materials. I have some really good data on moisture in materials and how that works, both from a fabricator standpoint and an assembly standpoint. But moving on to the presentation, this is an example of an RF board that's built separately from the digital part and then bonded together. And what's nice is you don't have the vias going all the way through. You keep the circuits separate unless you want them to, and then you make the interconnect with the Oremet. So you can see this is the Oremet bonding layer. This will be tacked to one side or the other and laser drilled, and then the paste is applied, and then when you laminate, you're making your electrical interconnects at the same time you're mechanically bonding the system together.
And you paste both sides?
No, typically you paste one side or the other.
Okay.
There are some nuances, there are some extensions of the technology where some fabricators are actually taking the pre-preg, the B stage, and they're creating kind of a free-form interconnect where they laser drill or mechanically drill and then apply the paste to the B stage, and now you have this sheet of material that's got the vias built in.
Okay.
So there are some novel ways to do this, but more traditionally, you're just tacking the B stage to one side or the other, laser drilling, applying the paste, and then bonding together.
So one thing I said earlier that keep the stack up symmetrical, when you use the Oremet paste, you can make all the different structures symmetrical, separate from each other, and then just bring them together. You don't have to worry about the bow and twist problem showing up.
Really?
Yeah, so you can have something that's all digital with lots of thin dielectrics and a radiator that's got these really thick dielectrics, and then you have the manifold in the middle, and you're just getting ground from top to bottom and whatever signals you need to do. And they can be completely mismatched, but each section is symmetrical. And then you just bring it together in, And the best thing is you don't put a drill, mechanical drill through it. If you got a bad top sub, throw it away, use another one. You're not committing the whole structure. If something went bad, you lose the whole thing. You could actually electrically test every one of those subs, know that they're good, and just laminate the good ones together and throw away the bad ones and not waste them.
And what's the cost factor?
Oh, you should see our safety people for that. I'm the technical guy.
There's a cost there?
Yeah, so, yeah, Ormet paste, you know, it's, there's a lot of technology that goes into manufacturing the paste, so the paste isn't inexpensive. It's very different than the conductive paste we use in printed electronics, where you have a metal flake and a binder system.
It's also two more processes you have to do.
Yes, yeah, the tacking and laser drill and paste fill, yes. Now, if you're doing a complex board, HDI board, you're actually eliminating some of the process steps as well. So you're trading something for something, right? You know, when you're plating vias shut, that could take a couple hours. So if you're not doing that multiple times over the course of the construction of the PCB, it could have a big advantage.
One of the other nice things is you don't have ground vias that are digital ground signals that are getting down into the RF layers. You can just Ormet paste the grounds that are okay to get down to the analog signals and block out on the top sub all the digital grounds, so there's no energy radiating into those vias. You only put Ormet paste vias that you want to connect the top sub to the bottom sub. All of the power and ground vias, you can just stop them at the other sub and not put an Ormet via. Instead of drilling traditional plated vias top to bottom, you can isolate and only bring the ground and the signals you want between subs. And it makes it a lot more, it reduces the noise.
Yeah, the frequencies wherever.
No, it's-
As far as isolation.
Yeah, there's isolation, yeah. You can isolate RF boards in an incredible way with this process.
No, but that's like I said, we're running at, most of our stuff is at 77. The easy stuff is 24, but
Yeah, it's tricky at best.
but it's, we have, yeah, fab definitely plays a big part, and it's iffy at best, you know. Thanks, Jerry.
You know, one of the things that's, you know, this technology compared to play-through holes have been around for probably close to 100 years in some fashion. Really became more mainstay, I would say, in the 40s and 50s. This technology is probably 20, 30 years old, so it's younger than plating, but it's not brand new. What's happening is, I think two things are happening right now is board shops are becoming more skilled at this, and the need is becoming more, relevant in the industry. It's becoming more important. So yeah, I think this is an area that's going to continue to grow. Yes.
So can we use Oremet paste instead of buried vias?
Instead of which one?
Buried. So buried.
Oh yes, yes. That is the idea. Is you would replace the buried via with the Ormet paste, which means you don't have electrolysis copper, you don't have electrolytic copper. Those processes for that particular via.
So it's like signal integrity wise, it's better to use Oremet paste or buried.
It can be. It can be a lot better. Again, you get rid of via stubs. You don't have basically the plating where you don't need it. It gives you a certain level of control where you put the conductors. So Mike has some great examples here. He helped with this presentation of where you can use the Ormet paste. And really, it just gives you a certain amount of design flexibility in how you form the vias. There's a lot of layers in that board. So again, you can break this up into more manageable components and then Ormet them together. So for thick boards or high density boards or both, boards that are both, you know, Ormet has a lot of potential.
You can use smaller vias instead of having to use large land areas and the large vias to get through a thick board.
Right, yeah, because of aspect ratio, right?
Right.
So if you're drilling through a thick board, you're going to need a certain diameter hole to make that work, to get the plating through it. And
Especially helps when you have a 24 millimeter space between your BGA patterns.
right, yeah.
Good point. I didn't see what size what's the minimum size on one of those pads.
So the copper particles in the paste are 8 micron. Now that doesn't mean you can do a 10 micron via. I would say the absolute limit's 50 micron, but that means you're stuck with a 50 micron dielectric with a 1:1 aspect ratio.
Right, right.
I don't recommend that. I like to see, you know, something.
Different PA systems.
Jeffrey, do you do that?
Orange okay.
I guess we need a break.
Now, like, bust into a flash dance.
1 o'clock.
All right. Is everyone awake now? Anyway,
So, yeah.
so really, I like to see something in the order of 8, 10 mils. That doesn't mean you have to use 8 or 10 mil dielectric. You can still do that in a 4 mil dielectric. It's just a whole lot easier to apply the paste, less can go wrong. But you don't want to exceed 1:1. And here's the other key point is, sometimes I've seen designers and fabricators forget their rules when it comes to fill of copper circuits. So let's say I have half-ounce circuits. I've electroplated, now I'm 1.5 mils thick, something in the order close to 1 ounce. I wouldn't use 1-ply prepreg to fill 1 ounce, you know, circuits. You know, because you a certain amount of resin. You don't want resin voids; they're pretty bad. So yeah, you want to use enough dielectric to fill the circuitry that's you're bonding together, and then make the via diameter 1:1 or less, so you get good Oremet interconnects. Just some more examples of where you could use the Oremet paste. And really the idea is that you can build these components and then bond them together at the end. And as Jerry pointed out, you can even electrically test your components and only use the ones that are good. Again, these slides will be available to you guys, and you'll be able to access some of this. So we've had some very good reliability testing with Ormet. We're still trying to get more data, but again, with the Oremet paste, you get rid of that electrolysis bond layer between your electrolytic copper and your foil copper. So the potential for some really good reliability gains. So this is getting a little bit onto the R&D side. So imagine a fabricator has a sheet of material where you've got copper foil and B stage bonded to a temporary carrier. You laser drill, add the paste, you laminate foil on top of it. Now you've got a double-sided core with your interconnects inside, print and etch that, and now you can put those together. So there's a lot of different potential, a lot of different ways this can go. And that's part of what we do at Insulectro is we try and develop these building blocks to give you guys more options. So that's just an example of, I think Monty, you did this. So yeah, we got some different things in development when it comes to Oremet. And with that, I think that concludes this presentation. Any more questions? Lots of good interaction with the audience, so I really appreciate you guys participating.
Well, we make sure there's some fabricators here, right?
Yeah.
So with that said, I'm going to turn this over to Jeffrey.